section 3.9, it's about linearization and differentials. In our lecture notes, it's 3.11 because the slides that comes from Thomas's calculus, I think they just forgot to change it. 3.11. Okay, so it's 3.9, linearization and differentials, in the new edition of our book. Let me show you some pictures about what we are doing in this section. Why do we need linearization and differentials? So let me open that up for you. Yeah, this is what I need actually. As I want you to just concentrate yourselves to these pictures, the graphs in here. What do we see in the first graph? In the first graph, we see that y is equal to x squared and the tangent line to this curve at the point 1, 1. Okay. In the second picture, we are just we are very much closer, more close to the 1, 1 now in the screen here. And do you see that when you get closer to this graph, tangent line and the original graph, which is y is equal to x squared, they are around the neighborhood of 1, 1. They are almost the same. Okay, let's tangent and curve very close throughout entire x interval. It is shown in here as if you, this is a closer look, okay, of the two. When you look at when you have a closer look to both of them, they coincide, okay, to us, to our eyes. It's like they both curves, the y is equal to x squared and the tangent line, they coincide to us. If this is a much closer view of it, so they exactly coincide. So what should we understand from this is, in this section we are going to be talking about linearization. What does it mean, linearization? So sometimes we might be given like a quadratic function like this, y is equal to x squared, and around some points we want to approximate the value, okay, for this function, but the function could be a difficult function to calculate, to find the value of. Therefore, instead of using the original function to get a closer value at a certain point, you just approximate that function, which is in this case y is equal to x squared, by its tangent line. Okay, so because if you get closer and closer to the point 1, 1 nearby, they coincide. So the values of these two functions actually, they coincide, they get very close to each other as well. So that's the idea in this section. Let me show you another picture here, because you need to get the picture idea first. So here, look, so this is the y is equal to f of x, this is the point A, f of a, and this is this tangent line. And see, around this A, these two curves, they get very close to each other. They almost take the same values around this point A. Okay, let's look at this example pictorially again. See, this blue curve is the y is equal to square root of 1 plus x, and we have a tangent line at 0 and we have a tangent line at 3. So for either, I mean, we have different tangent line, curves, tangent lines for each at each point, of course. And let's say if you want to approximate square root of 1 plus 0.005, so instead of using, I mean, square root of 1 plus 0.005, instead of using this square root function, we are going to just use the linear function instead, because the value around 0, they almost coincide, they get very close to each other. Okay, see, this is around 0, how close they are. Like, this is the tangent line, this is the original function. See, they almost coincide, the values are very close to each other, the y values. Yeah, therefore that's why we use the linear approximation of this function around the point 0. Or we can do this, they can ask a question about, for example, find the value of square root of 1 plus 3 plus square root of 3 plus 0.005 or 0.010. They can ask. Then around 3, this is the tangent line we have, and we are going to use this function to find the value instead of square root function, because calculating square root function is difficult. But it's easier to use the linearization function, which is this tangent line equation. So by using this idea, we have this linearization. Okay, so this tangent line, actually, I want you to look at this small picture here. This tangent line here, L of x, is the linearization function. Even if it's the tangent line to the curve at the point A, it is the linearization function. We call it linearization function to the curve here at the point A. So we can use this L instead of the original function when we want to find the values of f at points that are close to A. Okay, let's get this definition. If f is a differentiable function at x is equal to A, then the approximating function, which is a linear function now, this is a linear function, it's an approximating function, is the linearization of f at A. Okay, the approximation then, f of x is almost the same as L of x of f by L near A though. Okay, near A they are gonna the values are gonna be very close. But if you go away from A, then these values are not close to each other anymore. Okay, because if you stay away from A, there's a big distance among them. So you cannot really use this formula when you are far away from A. Okay, so yeah, this thing is called the standard linear approximation of f at A, and the point x equal to A is the center of the approximation. So there is a center for the approximation, which we get the tangent line equation and call it L, and then afterwards we just use this to get this approximation function relation, standard linear approximation of f at A. All right, that's the idea. Let me solve a problem in here. It's a nice example here. It says find a linearization of f at the point x is equal to 0. So what you're going to do is you're going to find the slope at x is equal to A. Okay, so our function is f is square root of 1 plus x, and we are going to find the linearization at x is equal to 0. So let's work on this here, in here. Let's see. Okay, so I'm going to, okay, example, this is example, let's see which example is this, example 1. This is example 1 in our book, yeah? So we are going to write it down here, okay. Okay. Find the linearization of f of x square root of 1 plus x square root of 1 plus x at x is equal to 0. Okay. Solution. All right, so what is L of x? We need to find it. What is L? Okay, at x is equal to 0. Yeah, L of x is the tangent line equation. So how would you find the tangent line equation? First of all, what is the point? Point is 0 to, we plug in 0 here, 1. Okay, or P01, yeah? Okay, and y minus 1 it's equal to m x minus 0. So what's m? M is equal to derivative at 1, yeah? What's the derivative then? Let's find out the derivative. The derivative of this is, okay, let's calculate the derivative here. Okay, the derivative is, okay, f of x is equal to 1 plus x to the 1 over 2. And then we use the power chain rule. Okay, derivative of this is 1 over 2, 1 plus x, decrease the power by 1, times the derivative of the inside function is 1. Okay, what's the value at 1? Pardon, at 0, I'm sorry. This should be 0. Let's erase, because x is 0, right? Okay, let's go down here. Okay, this is gonna give us what? 1 over 2. So here is the tangent line equation. Okay, let me write this down here. Y is equal to 1 over 2x plus 1. Okay, right? So then my L of x is x over 2 plus 1. Okay, so that's the linearization. That's the final answer. Okay, done. All right. Now we can say what's the standard approximation of f. We can say this is the final way, so we are going to say x over 2 plus 1 is approximately the same as square root of 1 plus x near x is equal to 0. So whenever you are near x is equal to 0, you can actually use x over 2 plus 1 instead. Okay, so this is our approximation, standard approximation. Okay, done. Okay, let me go to here, this table. For example, square root of 1 times 1.005 is the same as write 1 plus x over 2. Yeah, here x is 0.005, not 1.005, because this is like square root of 1 plus x, right? X is 0.005 over 2. This is the approximation function. We just plug in x as 0.005, and this is this much. But what is the exact value here? The exact value if you calculate square root of 1.005, it is this. I want you to see that how close they are. Look, 1.0025, 1.00249, so they are very close. So it's a good approximation near 0. Let's look at the second one, which is a square root of 1 plus 0.05. It is by standard approximation. This is approximately equal to 1 plus x over 2. X is 0.05. And if you calculate that, easily calculate that, 1.025. You can calculate this part by hand. But this one you cannot use by hand. You have to use calculator. So the true value is calculated by a calculator. This part is calculated by hand. Look at these two, how they are close to each other. How about square root of 1.2? It is the same as square root of 1 plus 0.2. So here x is 0.2, yeah? 1 plus x over 2. X is 0.2. This is 1.10, and the true value is very close to it. So this is a very useful approximation. Let's solve this. Let's find the linearization of the same f but at a different point 3. What we are going to do, we are going to again we are going to write the tangent line equation at that point, and then we are going to find L like this. We need f of 3 and we need f prime 3 here. By taking the derivative of that, we get 1 over 4. And then L becomes f of 3 plus m x minus 3, right? M is f prime 3, by the way. Yeah. All right, so this is the linearization, and if they ask about the linearization, what's f of 3.2, then we can use this the approximation to get the value. See, square root of 1 plus x. Let me move this towards right a little. Okay, square root of 1 plus 3.2. This is 5 over 4 plus 3 over 2 over 5. This comes from this linearization function. X is 3.2. Be careful here. Right, x is 3.2. So square root of 4 plus 2 that we are interested in. So we just find these values directly by hand even. And okay, the true value, you can get this value from the calculator. Look at how they close to each other. Okay. So we got that like that. Okay. Okay, let's see another example. We'll find the linearization of f cosine x at x is equal to pi over 2. You look at the graph here. This is our blue one, is our cosine. At pi over 2, we have the tangent line drawn here. And this is the tangent line equation, y is equal to negative x plus pi over 2. You can find this tangent line equation by using this formula, f of a plus f prime a x minus a, where a is pi over 2 here. Okay. And then f of pi over 2, which is cosine pi over 2, is 0. F prime is here negative sine x. At pi over 2, it is 1, negative 1. So x minus pi over 2. So we got that actually tangent line to the curve at pi over 2 is negative x plus pi over 2. And we call it a linearization function Lx. That's it. Yeah. Next, we are going to talk about the differentials. Differentials are very similar to what we are talking so far. It's just a different way of representing as same things. Look, Leibniz's notation I mentioned to you is dy dx when we are taking the derivative of right, and dy dx would be the derivative of y with respect to x, right? So as we have seen so far, it's like always ratio, but we can actually separate them, and we can consider each one as a variable. Okay. So, but where does it come from? Is it comes from? I'm going to show you a graph where it comes from. So, but roughly you can say that dy and dx separately, they are variables. Let's read the definition. Let y is equal to f of x be a differentiable function. Then the differential dx, a variable dx, is an independent variable, and the differential dy is just dy is equal to derivative of f times dx. Actually, I'm not planning on going into details of where it came from. The reason is I just want you to learn how we use it. So if you learn how we use it, that's good enough for us. For students who are curious, they can read the book and get more information about that, okay? So let's look at the example 4 on that. It says find dy if y is equal to x to the 5th power plus 37x, and b, find the value of dy when x is equal to 1 and dx is equal to 0.2. So what you do is you just apply the formula. F is here, x to the 5th power plus 37x, and dy is going to be the derivative times dx. Take the derivative of this, apply the power rule, 5x to the 4 plus 37. Okay, this is the derivative of f times dx. So it's very easy. In b, on the other hand, we are going to plug in x and dx values in there. So, so whenever x is 1, we put it in 5 times 1 to the 4 plus 37 times dx is 0.2. So the answer is the change in y, infinitesimal change in y, very small change in y, is 8.4 in that situation. Okay. Let's look at, so this graph is summarizing where it comes from. I'm going to tell you very quickly. So you can talk about delta L, change in L. L is the tangent line. Change in L is linear function that we know of is at a plus dx minus LA. Okay, so LA plus dx, you know that's what is the L function, you know that linearization function. So f of a plus f prime a, instead of x in there, you're going to put a plus dx minus a, minus L of a is just exactly f of a. So we get that. Alright, so from here, what you get is f prime, and then you're going to get dx in there, okay? So the graph relationship, this is our graph of f, and this is the tangent line. We have a to a plus dx. We go just dx many, but dx is the same as delta x variable. And then, on the other hand, delta y is f a plus dx minus f of a. You can consider dx as a plus delta x. And then delta a, on the other hand, of course, we consider dx as a small change in x, as I said, infinitesimally small. Okay. So from here, delta is f prime a dx. You find the corresponding f value here, a plus dx, as we found up here. Okay. So delta L, which is f prime a dx, is this much. Okay. And that's where we are going to get the dy. Okay. So we don't really get into too much detail on that. We are going to skip the details, but instead we will just see how we apply it. Let's look at the example 5. We can use the chain rule and other differentiation rules to find differentials of functions. For example, what's the differential of tangent 2x? Okay, so this is, we are going to use chain rule here. Take the derivative. So this is the composition of tan and 2x. Take the derivative of tan, which is secant squared, because tan 2x is our f here. Okay, the derivative of tan is secant squared, and keep the inside function times the differential of the inside function, which is 2 times dx. Okay, here we don't just say 1, 2 times dx. Okay, everything is in terms of differentials. Similarly, what's the differential of x over x plus 1? We are gonna, this is our f, so we just write the derivative of f prime times dx, but be careful here. We are going to this is the quotient rule. Take the derivative of the numerator times with the derivative of the, take the derivative of the numerator times the denominator, but the derivative of the numerator is dx in this case, minus keep x times the derivative of the denominator all over square of the denominator. Here we are going to have dx is all over, so this is dx plus 0. Just gather or factor out the x's from here, and then you get this cancels with that. We have dx over 1 over x plus 1 squared. Okay. Alright, so actually what we got here is exactly derivative of this times dx. If you want to try it out, you can, and you're going to get this answer, okay, instead of going through like that.